Welcome to the 34th lecture of this course. Today we will talk about the concept of reduction. Okay. So, what is reduction? So, reduction in computer science means to convert one problem to another. So, in our day to day life and also in computer science, often we try to solve one problem by reducing it to another problem. Okay. For example, if I want to in computer science, if I want to sort an array, I can and let us say somebody gives me a black box which is able to find the maximum element in an array. I can use that black box and sort the array. Okay, so, how do I do it? I do it by repeated application of this black box. So, first I feed my array to this black box, it will give me the maximum element. I keep the maximum element out, then I pass the remainder array, that is the array left without the maximum element again to this black box, which will give me the maximum element of this new smaller array, and that will be my second maximum, and I keep on doing this until my array becomes empty. Okay. So, this will allow me to sort an array. Also in for example, if I want to multiply two numbers, I can reduce it to the problem of addition. Okay. So, multiplying n times m essentially means that I want to add m to itself n times. Okay. So, if I can do addition, I can of course will be able to do multiplication. So, there are various other examples where we somewhat we always where we use reduction without often observing that this is what we are actually doing. So, what we will do today is we will formalize this concept. Okay, we will define precisely what we mean by reduction, and then we will see its application with respect to showing that problems are undecidable. Okay. So, informally, as I said, that reduction is converting one problem to another. Okay. So, now for the purpose of reduction, so when we reduce one problem to another, we will use the Turing machine model, but we will slightly modify the model. So, our Turing machine model will now contain 3 tapes. Okay. So, there will be an input tape, there will be a work tape, and there will be a output tape. Okay. Also in our finite control, so this is the finite control. Okay. In addition to all the states, we will assume that there is one state, okay, which we call the halting state. Okay. So, this is the convention that we use. So, what do these tapes signify? So, the input tape will signify the fact that it contains the input to the Turing machine. Okay. So, I can only read from the input tape, I cannot write anything to the input tape, and of course, I can scan it both sides, I can go back and forth on the input tape, but I cannot write anything other than the input. The work tape is where I perform my work to come up with a solution. So, I can write onto the work tape, I can read from the work tape, I can erase the work tape, I can do everything, and the output tape is a write only tape. So, the output tape has the property that I can only write bits to it, but I cannot read whatever I have written earlier. Okay. So, in some sense it is a one directional tape. So, whenever I write a bit, I move one cell to the right and I keep on doing it, I can never come back and read something. Okay. So, this input tape is as I said, so the input tape is read only, the output tape is write only, okay, and the work tape is of course read write. I can do both read as well as write. Now, what is the purpose of this halting state? So, what we want to do is that we want to compute functions, or we want to output functions of this form. Okay. So, let us look at a function which takes a string as an input, it can take any string, and it produces another string as an output. Okay. So, in the case of languages, one can think of languages as basically Boolean functions. So, functions which take a string as an input and produces 0 1. Okay. So, that is a special type of function. So, I can think of languages as Boolean functions, because whenever I have a string that is in the language, I will map it to 1, and whenever I have a string that is outside the language, I will map it to 0. Okay. So, languages are essentially equivalent to Boolean functions, where the Boolean functions are those where the right hand side has so basically functions of the form f going from sigma star to 0 1. So, these are Boolean functions. Now, I want to look at this general type of functions where actually I can write out a string. Okay. So, often this is necessary. For example, if I look at the sorting example, so in this case of sorting, I am given an array as an input, and I want to output another array which is the sorted array as output. Okay. So, I am not outputting a single bit, but I am actually outputting a string. So, it is essential that we have a way of computing such functions. So, this Turing machine, this particular type of Turing machine, this generalization I should say, is capable of doing it. So, what the Turing machine does is that it starts reading the input, it starts performing its computation, and during its computation it can write bits onto the output tape. It keeps on doing this, and finally, when the machine enters the halting state, I stop, and whatever is written on the output tape, that is the output of the Turing machine. Okay. So, let us call this a Turing machine with output. A Turing machine with output is a Turing machine that has a that has input, work, and output tapes as I showed, such that okay, for all x in sigma star, the Turing machine okay, computes a string y belonging to sigma star and before entering the halting state. Okay. So, this y I will call as the output of the Turing machine. Okay. So, now with this I define a computable function. So, a function f from sigma star to sigma star is said to be computable if there exists a Turing machine with output m such that for all x in sigma star m halts with f of x written on its output tape. Okay. So, this is when this happens, we say that the function f is a computable function. So, now we are in a position to define reduction. So, so let L1, L2 be two languages. Okay. We say that L1 reduces. So, there is a, so the reduces sign is basically, let me just say it, I can write it. So, we say that L1 reduces to L2. So, this is denoted as L1 with a less than or equal to sign L2. If there exists a computable function f such that for all x belonging to sigma star x belongs to L1 if and only if f of x belongs to L2. So, a reduction is basically a computable function which takes a string x and maps it to another string f of x such that it has the property that if x belongs to L1, then f of x must belong to L2, and if x does not belong to L1, then f of x should not belong to L2. Okay. So, pictorially I can we can represent this as follows. So, suppose this is our universe of all strings. Okay. Again we have the universe. So, f is a function which goes from sigma star to sigma star such that, so I have some subset of sigma star which is my language L1. So, this is language L1 and these are the strings which are not in L1, hence they are in L1 complement. Similarly, there is some subset which is L2 and L2 complement. So, we say that f is a reduction if L1 is mapped to, so let me put it here. So, if L1 is mapped to a some subset of L2, the entire L1, and the entire L1 complement is mapped to some subset of L2 complement. Okay. So, it is not necessary that every element in L2 or every element in L2 complement must have a pre-image. Okay. So, there can be elements outside also, there can be elements inside also. Okay. So, this is what a thing represents. So, f is a function which means not all element, f is a general function I should say, which means not all element in L2 or L2 complement has a pre-image. Okay. And so when now in our notation, okay, we had this small m as a subscript in our notation for reduction. So that m stands for many to one. So the m in stands for many to one. It essentially means that there can be many strings, let us say in L1, which is getting mapped to the same string in L2. Okay. For example, I can have string here and here. Okay, so maybe both of these get mapped to this guy. Okay. Same thing can happen here also. Okay. So it's a many to one function. So now why are reductions so interesting? The reason is the following proposition. So let L1 reduce to L2 and let's put it if. So if L1 reduces to L2 and L2 is decidable, then L1 is also decidable. Okay. So if I am able to reduce a language L1 to a language L2 and I know that L2 is decidable, then it means that L1 is also decidable. So why is this? So the proof is not difficult to see. So suppose I want to prove that L1 is decidable. So if I want to show L1 is decidable, I have to construct a Turing machine for L1. I know that L2 is decidable. So say L2 is okay. So since L2 is decidable, there exists a Turing machine M such that L2 equals L of M, and not only a Turing machine, it is a halting Turing machine. Okay. Now we will construct a Turing machine for L1. So what we will do in our Turing machine? So let us say I want to construct a Turing machine N for L1. So what the Turing machine N does is, given an input X, it first computes f of x. Okay. So why can we compute f of x? Because f is a reduction. Okay. So where f is the reduction function. Okay. So this is step 1. In step 2, you simulate M on f of x. If M accepts, okay, so if M accepts, then you accept, and if M rejects, then you reject. Okay. So, let us prove why this is correct. So, take any x. Suppose if x belongs to L1, okay, then after I compute f of x, because I know that f is a reduction, since x belongs to L1, f of x must belong to L2. Now, when I simulate M on f of x, since f of x belongs to L2, M accepts, hence I would accept. Okay. So, if x belongs to L1, I accept. Similarly, if x belongs to L1 complement, then here my f of x will belong to L2 complement. Hence, when I simulate M on f of x, it rejects. Hence, I finally reject. Okay. So, it is just a simple box which is doing two things. It is first computing f of x and then it is simulating M on f of x. Okay. So, that is the argument. So, now this has some interesting applications. So, as a corollary, we get two interesting, I mean we can say two things. So, first, if L1 reduces to L2, and L1 is undecidable, then L2 is also undecidable. Okay. So, now this gives me a mechanism to prove that a language is undecidable. So, if I want to show that a language is undecidable, all I have to do is that to reduce an undecidable language to my given language. If I can do that, then I would have succeeded in showing that my given language is also undecidable. Okay. And similar technique, I mean technique similar to what I have described here, can be used to show that if L1 reduces to L2 and L1 is not Turing recognizable, then L2 is also not Turing recognizable. Okay. So, the idea is the same, you can actually figure this out yourself. Okay. So, the key point here is that, so the key observation is that, so this is what you should always remember, that if L1 reduces to L2, okay, intuitively what this means is that then L2 is at least as hard as L1. Okay. So, the language L2 is either more harder than L1 or it is equivalent in hardness to L1. It cannot be easier than L1. Okay. So, that is intuitively what reduction means. So, this is what you should keep in mind. Okay. So, now let us look at a application of our this result. So, consider the language ETM. Okay. So, ETM is, so this is an example. So, ETM is encodings of Turing machine M such that M is a Turing machine and the language of M is empty. Okay, so, E stands for empty. So, this language we will prove that this is undecidable, and the way we will show this is undecidable is we will use this corollary here. So, we will take an undecidable problem. So, the problem that we will take is ATM bar. Okay. So, we will show that ATM complement reduces to ETM. So, not only will this prove that ETM is undecidable, it will also prove that ETM is not Turing recognizable, because ATM bar is also, we saw this last time, that ATM bar is not Turing recognizable. So, what is the idea? So, let me give the reduction. So, the reduction is nothing but giving a computable function. So, I want to design a function f, okay, that takes an instance of ATM bar, that takes an input which is from the universe of ATM bar, and it produces an instance of ETM, okay, such that if so, instance of ATM bar will be instances of the form m comma w, and instance of ETM will be just a simple machine m. Okay. So, I will take as input encoding of a machine, let us say m comma w, and I will produce as output, let us say I will give this another name n, such that if m does not accept w, then this language is empty, the language of n, and if m accepts w, then the language of n is not empty. Okay. So, that is what I am going to do. So, how do we design the machine? So, what we do at the beginning is, okay, so design n as follows. So, here is what n will do. So, on an input x, so x is the input to n. So, I have to define the Turing machine n. Okay. So, I have to define that what this Turing machine is going to do on every input. Okay. For example, if I am given an input x, what should the behavior of n be? So, what n will do is that first n ignores x. Okay. So, n would simulate m on w. Okay. If m accepts w, then accept if x is equal to w, else reject. Okay. So, let us look at representation. So, I have my, so I want to, so this is my reduction f that I want to design. Inside this I am designing this machine n. Okay. So, what n does is that, so f takes as input two things, it takes an m and it takes a w, and n is taking some x as input. So, what it does is that first it will simulate m on w. If this accepts and if this rejects, we do two things. So, if this rejects, then n will reject, okay. And if m accepts, then check if, okay. So, check if x equals w. If this accepts, then accept, else reject. Okay. So, now let us try to understand, and finally f will output the machine n. Okay. So, let us try to understand what is happening. So, suppose if M accepts W. So, if M accepts W, observe that here I would accept W, then the machine N is going to check if X is equal to W. If X is not W, it is anyway going to reject. So, which are the which strings X will N end up accepting? So, N will accept only the string W. Okay. So, then the language of N is going to consist of only the string W, that is the only string that it will accept. On the other hand, if M does not accept W, then so if M does not accept W, if M is rejecting or if M is going into an infinite loop, I will directly anyway reject or go into an infinite loop. In other words, it will not accept that X. So, in other words, the language of N will be the empty set. Okay. So, now I have shown that therefore, ATM bar reduces to ETM, because if M does not accept W, then I am outputting a machine N whose language is empty, as it is the definition of ETM, and if M accepts W, I am outputting a Turing machine whose language is non-empty. Okay. So, that is a no instance. So, here I am outputting a yes instance, here I am outputting a no instance. Therefore, I have this reduction which proves that ETM is undecidable. Okay. So, I will stop here. Next time we will look at more examples.